pH titration is we use a beaker for the titration, and then we'll have some acid in here. And we'll put the base in the burette here. But rather than titrating it to like the indicator, which most people are familiar with, like the pink color that persists, what we're going to do is we're going to put a pH probe in here. And we're going to monitor the pH throughout the titration. And what we're going to do is we're going to plot the pH as a function of milliliters of base. And I'll talk about it in more detail tomorrow, but basically we're going to be collecting points along with titration so we can map out what this looks like. But we have to make sure that the points are not too far spaced apart and not too close together. If they're too close together, then we're spending a lot of time collecting data, maybe needlessly. However, what's too close together in one spot may be too far apart in another spot. And so there's going to be a steep rise. And this steep rise in the pH, what we have to do is we have to collect a lot of data, like drop by drop. And then once we're past that, then we can widen it out depending on the structural features of the curve. And so we have to play around with the intervals here. Maybe at the beginning here, 1 milliliter intervals might be enough. But as we close to this rise here, we need to do drop by drop, and see, because this rise can occur within 2 drops, and then we might miss it entirely taking 1 milliliter intervals. And so the point of this is to adjust our spacing between the data points so that we can perfectly, or to not perfect, but as best as we can map out this titration curve. Problem is, why don't we do the whole thing drop by drop, and that way we don't have to worry about it. But the problem here is we're going out to, let's say, 45 milliliters, or so, and each drop has 20 milliliters, and so that would be 900 drops. And think about recording 900 pH readings. You gotta wait until that pH reader stabilizes. It would just take way too long. And so we're going to do a trial titration first. The trial titration is just so we can find out where the steep rise is. And so we do a trial titration and figure it out. The trial titration, we're just going to titrate to phenolphthalein. The pink color, you go from colorless. Have you guys done titration with phenolphthalein?
I've seen videos of it.
Okay. Well, we're going to do a quick titration with phenolphthalein, just, to hear. Phenolphthalein will change color in this region where we have the steep rise, so then we know how many milliliters we use for a given amount of acid. The acid that we're using is going to be a solid acid, which is oxalic acid. We'll have to dissolve that in water here. All right, so this is just for tomorrow's lab, and I'll talk more about it at the beginning of lab tomorrow. Okay, any questions?
Professor, someone has a question.
Okay, go ahead.
I just want to know what days that I have to do.
The homework for chapter 15 is due on Thursday. Also, if you're not aware, I've been going through the homework in these sessions I've been holding. They're in the announcements here. I don't know how I can prevent this. You guys know? So these chapter 15 series, they're all there's recordings of these. I know the attendance has been pretty small, but you can check out the recording. I know the time is not very convenient, but that's the best time that I can arrange for myself. Okay, so the homework's due then. And then I went through a bunch of homework problems already. I think we're up to 70 something now in these. Not every single problem, just the ones that people were asking about. All right, let's take a look at chapter 16. And we were looking at a problem the other day, which was, what is the pH of 1 × 10 to the minus 8 molar HCl? So normally when we're thinking about 1 × 10 to the minus 8 molar HCl, this HCl is a strong acid. And the strong acids are going to consist of H plus and Cl minus. And so this is going to be 1 × 10 to the minus 8 molar H plus. Strong acids completely dissociate, ionize, or hydrolyze in water. And so that's what I should end up with. And so the power of this is 8, so, and then we have 1 sig fig, so it's 8.0. That would be it. But the problem with this was what? This is basic, and it's impossible. This pH is impossible. And so the one thing I'm missing is that this isn't the only source of hydrogen ion. There's one more source of hydrogen ion. What is that? Water. And so when I have multiple sources, then what I have is, this is an example of multiple equilibria. With multiple equilibria, there are different methods that we use to solve multiple equilibria. And so the methods that we use, the first one is stepwise. So usually you start off with the strongest, and then you go weaker and weaker. And so start with the strongest as step 1. And then you go weaker and weaker for step 2. There could be more than weaker. Another way that we could solve these is we can solve them simultaneous. The third way is if they're not related. If they're not related, then we could solve these as independent and solve separately. What I mean by not related is they don't share a common species or common ion. There's nothing in common with the two equilibria. And so the easiest method is going to be stepwise, but it doesn't always work. So this is easiest. But the problem is that it doesn't always work, whereas simultaneous always works, but it's more difficult. more difficult. So let me give you some examples of stepwise and simultaneous here that we'll encounter. This one we can solve stepwise, and it works fine. And so, stepwise involves the strongest species, which would be hydrochloric acid, and the other species that gives hydronium or H plus is water. And so we'll take a look at step one here first. It would be the HCl plus H2O. Rather than doing an ionization like I did over there, we're going to do hydrolysis. This is going to form hydronium plus chloride. Now, strong acids react completely. And so what we say here is we don't necessarily have to give a number to K. Whenever we have a strong species, we say like strong plus water in this case. We say that K is very large. What that means is it's all product. All product. All product. And so what I'm going to do here is initially, I'm going to do an ice table, just in general. Your book doesn't do this. We'll just skip this ice table here. But we start off with 1 times 10 to the minus 8 molar, and we assume that nothing's hydrolyzed yet. And so this is what we have in solution. And then if it's all product, we're going to lose all the reactants. So this is going to be minus 1 times 10 to the minus 8 molar, and that's going to give us 0 molar. So we have no more reactant left. And we converted all to product. That is, if there's no limiting reagent, excess reagent scenario. If there's a limiting reagent excess scenario, then we're going to have some excess reagent left over there. So we end up with this, 1 times 10 to the minus 8 molar. Hydronium, 1 times 10 to the minus 8 molar. Chloride. Okay, then we move on to step 2. Step 2 is going to be water. And so it's going to be H2O liquid colliding with H2O liquid. That's going to contribute some more hydronium. Now, how much hydronium does this contribute? And pure water contributes 10 to the minus 7 molar, pH 7, 10 to the minus 7 molar. But when we have what's called common ion present, it's going to contribute less. It's going to contribute less because I made a mistake. So H minus, right? Thanks. This is called common ion here. And so there is a common species between these two equilibria, and that is hydronium. And so this is stepwise. So what we're going to do is we're going to drop the hydronium from step 1 down to step 2, and then we'll have this here, 1 times 10 to the minus 8 molar. The hydroxide is going to be 0 molar here. Now, what we're going to do is, this is from the HCl, step 1. So what we're going to do is we're going to figure out how much additional hydronium we're going to add from step 2. And so that's going to be the change here. The change is going to be plus X molar. X molar is the hydronium from water. The 1 times 10 to the minus 8 molar is the hydronium from HCl. And then we're also going to get hydroxide. Whenever we form hydronium, we'll also form hydroxide. Now, this is called the common ion effect. Well, what is the common ion effect? This isn't the common. The common ion effect is that we're going to get a smaller than 10 to the minus 7 molar. If this were 0 and 0 here, we get 10 to the minus 7 molar, 10 to the minus 7 molar. But since we already have a significant amount of hydronium, we're going to get much smaller numbers here. And so we're going to get less than 10 to the minus 7 molar. And so we're going to figure out what that is. And so this is going to be 1 times 10 to the minus 8 plus x molar. This is going to be x molar here. Now, K for this, most people memorize. This is KW at 25 degrees C. KW at 25 degrees C is 1.0 times 10 to the minus 14. Now, this is significant because it doesn't matter, you know, if we're dealing with a solution or pure water, you know, KW is always going to be the same, you know, because if we're dealing with a solution and that solution impacts the hydrogen and hydroxide, we'll see the common ion effect like this. If we're dealing with pure water, then there's nothing in there. We'll have something like this. And so KW is equal to the hydronium and hydroxide. And so what this means is that there's hydronium and hydroxide present in all solutions. And what makes an acidic solution is this. What makes an acidic solution is, well, there's strong acids and strong bases present, but what makes an acidic solution acidic is we have more hydronium than hydroxide. A neutral solution has equal amounts, 10 to the minus 7 and 10 to the minus 7, and a basic solution has more hydroxide than hydronium. And so here, this is going to equal 1 times 10 to the minus 8 plus x times x. Now, this is kind of small. You know, our initial is quite small. The simplifying assumption works best if the initial is large, but let's go ahead and try it anyway. So if I try my simplifying assumption, SA, what I'm going to get is 1 times 10 to the minus 8 times x. And that means x is equal to, well, divide that, that's 8. It's going to be 6. So 1 times 10 to the minus 6. That's what x is equal to. Now, if x is equal, what was the percent change? Well, if we start off with 10 to the minus 8 and the change was 10 to the minus 6, the change is bigger than what we started off with. And that change is going to be, well, 10 squared, it'd be 1,000% change. And so this is 1,000% change. So unfortunately, the simplifying assumption fails. And even though, look at the K is very small. We expect very little forward, but since we started off with such a little quantity initial, then it didn't work out so well. And so the point here is that the simplifying assumption works best when K in the direction of the change is very small. That's checked, that's good. And the initial's big or significant. Well, the initial here is very small. So it failed on that point. So this is why the simplifying assumption failed here, even though the K was looking good for this particular reaction. So what we have to do is we have to do the quadratic then. Well, quadratic is not too bad. We're going to get at least solving it in quadratic form is not too bad. Plus 1 times 10 to the minus 8 x minus 1.0 times 10 to the negative 14 equals 0. How good are these quadratic solvers? Well, I just picked the one off, you know, the Google search here. Actually, the quadratic solver on the calculator, the Casio, is pretty good. You know, I've gotten good results off that one. But it turns out these quadratic solvers aren't the greatest. Last night's session, we've looked at calculation with one of these quadratic formula calculators, and the answer came out wrong. Yeah. And so they programmed this. So as an alternative to that, you know, there's one that's pretty good is, but I use Wolfram Alpha for a lot of math. And this is nice. So I'm going to just plug it in here. So we're going to get x squared x squared plus 1 times 10 to the minus 8x plus 1 times 10 to the minus 8x. That's how you input this here. Minus 1 times 10 to the minus 14 is equal to 0. Let's see if this works for the math input. I guess I didn't input it correctly. Oh, that does look right. It doesn't tell me what that is there. 1 times 10. What's this one here? Well, they give me this so they don't have to round it. I don't want to have to calculate it. All right, Wolfram Alpha is giving me these. I don't want it in some kind of fractional form. So I'm actually going to go back to this. This one should work though. It was just that complicated one that we did earlier. 1 last night times 10 to the minus 8, and then negative 1 times 10 to the negative 14. All right. So here I have a negative. It can't be negative because I can't have it. Can it be negative? Let's see what no, it can't be negative. There can't be a negative hydroxide concentration. Because that would require weighing negative grams. I mean, how could you weigh, like, you have a gold coin and weigh negative 1 gram? How could you have that? It's impossible. So we can't have a negative. It's got to be this 1.0 times 10 to the negative 8. Okay. So that's equal to 1.0 times 10 to the negative 8. Oops, 9.5. I'm sorry. X is equal to 9.5. 9.51249. 9.51249 times 10 to the negative 8. You know, the calculator can get that. Unfortunately, you can't use this on the test, so we'll come out on the test.
Is the test on Thursday?
Test is on Thursday. That's right. Okay, so let's go ahead and calculate the equilibrium concentration. So here, this is going to equal the 1 times 10 to the minus 8 molar from the step 1. So I had 1 times 10 to the minus 8. I'm going to just write this in decimal. Well, actually, both of these are 10 to the minus 8, huh? I'll just leave it. 1 times 10 to the minus 8 from step 1. And then how much did I add from step 2? In step 2, I added 9.51 times 10. I'll just carry 2 extra digits here, times 10 to the minus 8. Maybe I'll carry 3 sig figs, 2 sig figs. I'll carry 1 more. We'll carry 2 extra digits here. And so if you look at this, step 1 only produced 1. Step 2 produced about 10. And so step 2 produced about 10 times as much hydronium as step 1. And so altogether, this is going to come out to 10.512 times 10 to the minus 8 molar. And then how much hydroxide did we produce? We didn't produce much, 9.51 times, I'll carry 2, 512 times 10 to the minus 8 molar. Actually, it did produce a significant amount compared to 0. All right, so let's check our K value here. So if we check our K value, K is just going to be equal to that times that. That is 10.512 times 10 minus 8. Times 9.512 times 10 minus 8. And I get 1 times 10 to the negative 14. So we're good. So this is the very good effect. Put the two back together and you can see value. Yeah, just see if these two multiply to K value. So, so now we have the total hydronium. The total hydronium is equal to the hydronium from step 1 plus the hydronium from step 2. And that came out to 10.512 times 10 minus 8. And therefore the pH is the negative log of the total hydronium in solution, which is going to equal, let's just plug that in, 10.512 log 6.978. 6.978. How many sig figs are we going to be allowed? Looks like I only have one sig fig here. That's going to give me 2 sig figs here at the end, so I'm going to be allowed 2 sig figs. So this is going to be 6.99. This pH is almost neutral. You see? In other words, there's so little strong acid in there, it's almost like neutral water. It's just trace amounts. So this is why I said, if I had a glass of this, I'd drink it, because there's practically no acid in there. 10 minus 8. All right, the stepwise works in this case. The stepwise works because of this. Stepwise works because step 2 does not upset step 1. So what happens is this, Le Chatelier's principle. Le Chatelier's principle says if I increase the hydronium, say, which direction does the equilibrium shift? To the left. And so what I did was I added about 10 times more hydronium to step 1. And so that should shift it to the left. But when we have a cave that's very large, this is not perturbed by Le Chatelier's principle. So even if I increase the amount of chloride, will that reduce the hydronium? So let's say, you have too much stomach acid. If you increase the amount of chloride, will that decrease the amount of hydronium? So in other words, can you use table salt, sodium chloride, as antacid? Will it be a very good or very effective antacid? No, it would be totally ineffective. And so even if we increase the chloride a huge amount, let's say you add a whole bunch of salt, will it shift this to the left and decrease, the hydronium, which will increase the pH? No. And so, does not perturb. This is not perturbed by Le Chatelier's principle.
What do you consider a very large p-value?
Literally, do you see the table there? The middle one?
Yes.
Look at the K on the right-hand column and the left side. What does it say?
Very large.
It says very large. That's what I consider a very large value. It's literally going to say very large. There's actually a number for it. It's not infinite. And that number is surprisingly not that large. It's like for HCl is like 10 to the 15th or something, 10 to the 16th, But the easiest way for our calculations is to treat it like this. And then we let things equilibrate here at the end. And so, yeah, it's going to literally say very large. Let's take a look at where the stepwise method fails. The stepwise method is going to fail when step 2 perturbs step 1 by Le Chatelier's shift. And so let's pick an acid here. Pick what acid? The acid that I want to pick is not there, it looks like. So H2CO3 is fine, except it has more steps. And so I think the one I want to do is, let's just have it as one step, and then we'll do something like H2CO3 later. The one that I want to show that stepwise fails for. But we could do something with H2CO3 where stepwise works. Yeah. Though I don't know what saturated solution H2CO3 has. 6.8 times 10 to the minus 10. Let's look at hydrocyanic acid. I think this is what the book uses. So this example of stepwise fails. Actually, we could use hydrofluoric acid too. What is hydrofluoric acid? 3.5 times 10. Hydrofluoric acid is just a little bit stronger. Just use hydrocyanic acid. So we're going to do the exact same problem here. It's going to be 1 times 10 to the minus 8 molar HCN. But HCN is a weak acid, and so it doesn't completely dissociate or completely ionize in solution. So we have to figure it out. And so what we're going to do is, HCN is a stronger acid than water. So step 1 is going to be water. Step 2 will be KW. And so this will be step 1. And then step 2 will be KW, which will be the other source of hydronium in this. And so here, so let's go to step 1, the HCN. Now, this is the strongest acid. And when we're dealing with strong acids and bases, we take the strongest acid and react it with the strongest base. So what is the strongest base present? Water. Okay. So what happens is the most likely acid-base reaction to occur will be between HCN and the base water. And this is going to produce hydronium and cyanide. Now we need K. This is K for acid. K for acids is acid plus water. You know, water is usually the strongest base present if you just have an acid solution. So this is what we call the acid ionization constant, or the acid hydrolysis constant. Most people just call it the acid ionization constant. And it's just a Kc. It's equal to Kc, basically. So if I look at the Ka value, which I just searched for, 6.8 times 10 to the minus 10. One, that tells me it's a very weak acid. I mean, 10 to the minus 10. What's water? Water is extremely weak acid, and what is, essentially this is Ka for water. And it's 1 times 10 to the minus 14. So that's 10 to the minus 10, water is 10 to the minus 14. Water is like 4 orders of magnitude less. But this is pretty small. And so HCN is not a very good acid. All right, so I don't expect to produce all that much hydronium. So I'm going to start out with 1 times 10 to the minus 8 molar. Nothing here, nothing here, nothing here. We always assume that nothing's happened. And just makes the calculation easier. Okay, then the change, it's not going to be complete. I'm just going to minus X molar, plus X molar, plus X molar. And so at equilibrium, I'm going to get 1 times 10 to the minus 8 minus X molar, and X molar. Now, this is going to equal the hydronium times the cyanide divided by the HCN. Okay, so the hydronium is going to be X, the cyanide is going to be X, so that's going to give me X squared top, and this is going to be 1 times 10 to the minus 8 minus X on the bottom. I could try the simplifying assumption, because the simplifying, you might as well just try it and see. If it fails, it fails. If it works, great. We save some time. I already know it's going to fail, but can you see it's going to fail? If you can't see it's going to fail, just try it and see. The reason is again, K is good. X should be very small because this is such a weak acid. But the problem is the initial. The initial is so small that even if X is small, it might be significant. And so that's the problem we have here with this. And so if I try the SA, then that goes to X squared over 1 times 10 to the minus 8. And so this will give us that will give us 10 to the minus 2. So 6.8 times 10 to the minus 2. 6.8 times 10 to the minus 2, and then take the square root of that. 0.26. So if I use my simplifying assumption, I get X equal to 0.260. Is that small compared to 10 to the minus 8? This is 10 to the minus 1. This is very large. This is like a 1,000,000% change or something like that, right? Or more. This is like a 10 million% change. So it failed. It's all right. Did it take us much time to see that it failed? No, it didn't. So anyway, we have to do the quadratic. And so, okay, let's do the quadratic here. This one. Let's get into quadratic form. So getting into quadratic form, this is going to come out X squared plus 6.8 times 10 to the minus 10 X minus 1 times 10 to the minus 8 is equal to 0. So we use the calculator here. Yeah, 1 and then 6.8 times 10 to the minus 10. And then -1 times 10 to the minus 8. So here I have 9.9. 9.9997 times 10 to the minus 5. I have to be careful here. I don't want too much rounding, so let's go ahead and I'm going to carry some extra digits. 9.949 after the decimal. 1, 2, 3, 4, and then a 7 times 10 to the negative 5. Could that be right? So if I go back over here, I have 1 times 10 to the negative 8 minus, what would this be times 10 to the negative 8? Negative 6, negative 7, negative 8. This would be minus 9,999.97 times 10 to the minus 8. There's a big problem with this. And the big problem is what? That's negative. I'm going to come out with negative 9,998.97 times 10 to the minus 8 molar. I can't have negative molarities at equilibrium. So I don't know what happened here. Something got screwed up.
I think when you put it into the equation, you missed a step. 1 times 10 to the minus 8 times 6.8.
Oh yeah, you're right. I forgot that step.
6.8 times 10 to the minus 18.
Yeah. So it should be 6.8 times 10 to the minus 18 as my last one. But anyway, fortunately it caught my mistake here. Hopefully it would have caught it at the end. But I did make a mistake here. That is, this is not 1 times, this is 6.8 times 10 minus 18. Okay, so let's go ahead and fix that here. 6.8. Still wrong, but I see the mistake here. 18. Okay, now this looks reasonable. 10 to the negative 9, so it's got to be smaller. Yeah. So it's 2.2897 times 10 to the negative 9. 2.2897 times 10 to the negative 9. I'll just carry some extra digits, not a whole lot. Okay, so I'm going to make this 10 to the negative 8. So that's going to make it 0.2822897 times 10 to the negative 8. So what did that come out to? I guess I could just carry the 5. Just carry the 5. And so I'm going to take 1 minus 0.228975. And there's 0.77, 10, 25. 0.77, 10, 25 times 10 to the minus 8 molar. Okay, the hydronium over here should be 2.28975 times 10 to the minus 9 molar, and the cyanide should be the same. All right, now what we should do is we should double check this. And double check. That is, I'm going to plug this into K, see if it works. So I'll take the 2.28975 times 10 minus 9 and square it. Two point 28975 times 10 minus 9. Square that. And divide it by 0.771 1025. 0.77 1025. 10 minus 8. I get 6.79 times 10 to the minus 3, 6, 9, 10. Times 10 minus 10. And so this looks good. Yeah. So we're good. All right, now this is the amount of hydronium we generated from step 1. It's actually a pretty high percent ionization. It's, when we look at it, we started off with 1, we lost 0.228. What percentage did we lose? So the way you do this is make this 100. If I make this 100, that makes it 22.8. And so if I lose 22.8, then that's a 22.8% change. And so the percent ionization varies. It turns out it looks like this. This will be just a side topic here. Let me erase this. When we look at weak acids, and we look at the percent ionization or hydrolysis or dissociation versus the concentration of that acid, which we call HA, just a generic acid. This is weak. When we look at the percent ionization of weak acid, the percent ionization increases as the concentration decreases. Now, higher concentrations, the percent ionization is low. For a strong acid, the percent ionization doesn't change. And so for a strong acid, the percent ionization is 100% throughout. And so regardless of what the concentration of a strong acid is, we always say it's going to be 100% ionized. For weak acids, we don't know what the percent ionization is going to be. We have to calculate it. So just calculate it here. It's 22.8%. See that? Okay. All right, now what do we do? Yeah, so now we have to figure out how much comes from water, KW. And so, it'll be step 2. So step 2 is going to be H2O liquid plus H2O liquid. Gives us hydronium and hydroxide. This is KW. And the common species here, in this case the ion, the common ion here is hydronium. So we're going to take all the hydronium that was generated in step 1 and then start with that in step 2. So this will be the hydronium from step 1, which is going to be 2.28975 times 10 to the minus 9 molar. Step 1 did not produce any hydroxide, so this is going to be 0 molar. be our initial. The change, we're assuming that no water is hydrolyzed yet. And so there's no hydronium or hydroxide produced by the water. And so the change here is we're just going to go plus X molar here. And so then at equilibrium, we're going to have the hydronium from step 1, the 2.28975 times 10 to the minus 9, plus the hydronium from step 2, which was X. We've yet to figure out what that is. And then we're going to get some hydroxide as well from waters. Dissociating. All right, so let's go ahead and calculate our Kw here. So Kw is equal to the hydronium times the hydroxide. It's going to equal 2.28975 times 10 to the minus 9 plus X times X. This is equal to 1.0 times 10 to the minus 14 at 25 degrees C. So we've got to assume we're doing this at 25 degrees C. All right, we'll get this into quadratic form. So this is going to be x squared plus 2.28975 times 10 to the minus 9x. Then I have to multiply these together, which is going to give me minus. Actually, I don't have to multiply those together. I just subtract this. Minus 1.0 times 10 to the negative 14. This is equal to 0. All right, so let's go back to the quadratic solver. A is 1, B is 2.28975, 2.28, no, come on, what's wrong with this? Okay, now 2.28975 times 10 to the minus 9. All right, C is equal to negative 1 times 10 to the negative 14, negative 1 e to the minus 14. Let's calculate that. All right, so it comes out to 9.88617 times 10 to the minus 8. $9.88617. Okay, I'm going to make that 10 to the minus 9. So make that 10 to the minus 9, it's going to be, what, 98? Just then make this one smaller, make this one bigger. Okay, so this is going to equal the 2.28975 times 10 to the minus 9 plus x. This is our x here from step 2. And so this is going to be plus 98.8617 times 10 to the minus 9. And so what does that give us here? So I'm carrying a lot. You know, you don't have to carry this many digits because it just takes time, right? You carry at least 1 or 2 digits extra, you should be okay for most problems. Sometimes you'll have to carry more because it comes off a little bit, 98.8617. 101.15145. So the total I get is 101.15145 molar, times 10 to the minus 9 molar. Okay, and then this is our x, so So this is equal to 9.88617 times 10 to the negative 8 molar. Okay, then we're going to check our K. So I'm going to take this times this, 9.88617 times 10 to the negative 8. And I get 1.00 times 10 to the negative 14. So that's good. That checks out, right? Pretty much right on. But what we have to realize is that both of these equilibria are in the same container. In fact, they're both in the same solution. So this is the new hydronium concentration I have. And that means that this hydronium concentration is no longer valid. Right? And so this is how step 1 perturbs step 2. Step 1 is going to perturb step 2 by changing the total hydronium. So we started off with about 2, and then we increased it to 101. Well, Le Chatelier's principle says, well, that's not sustainable because this was equilibrium here. Remember we checked the K, and the K was at equilibrium. The K was at equilibrium. And so K was at equilibrium, but now it's no longer going to be at equilibrium because this is no longer valid. And so what we have here is this one increased from step 1 to 101.15145 times 10 to the minus 9 molar. And so increased. So what that means is that we're no longer at equilibrium because, well, this one's still 2.28. Actually, I should say this one didn't change. This is still 2.28975. It's 10 to the minus 9 molar. Well, that's okay. We can fix it, right? We'll just do step 3. If we do step 3, then we'll just readjust these concentrations to reach equilibrium again. That is, we'll do a Le Chatelier shift left and then adjust it. But if I change this again to adjust it so it fits this equilibrium, what do you think is going to happen to the first equilibrium? It changes that. And so we're in a circular argument where step 2 will perturb step 1. Then we go back to fix step 1 and that perturbs step 2, and we can't solve this stepwise. You see, this is impossible to solve. Impossible to solve stepwise. Because what happened is we're going to just go in circles and not get any answer. So what you need to do is you need to recognize that stepwise failed. And so our answer here is stepwise failed. I'm sorry? Oh, K was at equilibrium, but now is no longer, after step. K was at equilibrium at the end of step 1, but is no longer at the end of step 2. And of step 2 because we just changed the amount of hydronium. Does that make sense? Uh-huh.
I don't really understand how it changed because it seems like the K at the end is pretty much the same as the K at the beginning.
Okay, I didn't recalculate it. Let's recalculate K with the new hydronium. So here's a new hydronium. And so I'm going to recalculate K now. This was the K at the end of step 1. Now this is going to be the K at the end of step 2. The K at the end of step 2 is going to be the hydronium concentration, which is the 101.15145 times 10 to the minus 9, times the cyanide concentration, which stayed the same, 2.28975 times 10 to the minus 9, divided by the HCN concentration, which is 0.77120025 times 10 to the minus 8. And so let's see what K comes out to when we recalculate K with the new hydronium concentration. And so that's going to be 101.15145 times 10 to the minus 9 times 2.28975 times 10 to the minus 9 divided by 0.771025 times 10 to the minus 8. So my K value comes out to 3.003 times 10 to the 6, 7, 8 times 10 to the minus 8. Does this K value match our K value? No. This is not equal to 6.8 times 10 to the minus 10. So it's no longer in equilibrium. In fact, this is too big. That means it's going to shift left. This is too big. Shift left. So what we could do is we could say, okay, fine, shift left. This is going to be plus x minus x minus x, but then we run into circles. All right, so for Chem 1B, what we have to do is we're going to be solving a lot of problems using stepwise method. But we have to be able to recognize when the stepwise method is going to fail. And so this is recognizing that the stepwise fails. Each time we do a problem, we check, does this step perturb the previous step? If it does perturb it, is it going to make any difference? For example, in the previous one, it didn't make any difference. Why? Yes, because K is very large. When K is very large, it's not perturbed by Le Chatelier's. And so in this case, it did not perturb it. In this case, it does perturb it. And so what we have to recognize is, in this case, it's okay to do stepwise because it's the easiest. Here, it's not okay to do the stepwise. What do we have to do? Well, we have to do the simultaneous, and we try to avoid the simultaneous because it's a lot of work. And stepwise is usually enough, good enough. And in fact, all multiple equilibria should be solved simultaneously. It's just, the math is too much. And so we just don't want to do it. So we should be solving even this one simultaneously, but we're trying to do the minimum amount of work possible and not make our life difficult. Well, it's not terribly difficult to solve simultaneous. Let's just take a look at this one. How would we set this up and how would we solve this simultaneously? sometimes, we can kind of predict, the KW is not going to be a very significant contributor to hydronium, just by looking at the number. And so sometimes we can just eliminate, even if we do it stepwise, we can eliminate certain steps because they aren't going to be significant contributors to the hydronium, just based on the numbers. And if we can eliminate steps, then that saves you a lot of time. So when we do simultaneous, we have to set these up, simultaneously, basically. And so we're going to have HCN plus H2O liquid. This goes to hydronium plus cyanide. And then we're going to have H2O liquid plus H2O liquid. This is going to go to hydronium plus hydroxide. Well, how should we set this up now? Well, this has got to be kind of, normally what we think is nothing's happened yet, and then we're just going to go ahead and do this. And so this is going to be a little bit weird because from the perspective of reaction 1 here, reaction 2 has already occurred, but nothing's happened for reaction 1. So what we're going to do is we say reaction 2 has already occurred, but nothing's happened for reaction 1. And so what that means is I'm going to have 1 times 10 to the minus 8 molar here, H2O liquid. Now reaction 2 has already occurred, producing some hydronium. Well, how much hydronium did reaction 2 produce? Well, we don't know, because the amount of hydronium in reaction 2 is not going to be 10 to the minus 7 molar. Why? It's not going to be 10 to the minus 7 molar because of reaction 1 is present. And so what we're going to say is Y molar is going to be the amount of hydronium produced from reaction 1. And the cyanide is going to be 0 molar. And so now we're going to figure out how much additional hydronium we're going to get from reaction 1. And so this is going to be minus X molar, plus X molar, plus X molar. So at equilibrium, what we're going to get is 1 times 10 to the minus 8 minus X molar, Y plus X molar. So Y is the amount of hydronium that came from reaction 2. X is the additional hydronium we're going to get on top of that. And then the cyanide would be X molar here. Now, from the perspective of reaction 2, we're going to assume that reaction 2 hasn't happened, but reaction 1 has already happened. So both of these can't be simultaneously true, but it's just going to make the math easier. So if that's the case, then reaction 1 has already happened. And how much hydronium did reaction 1 produce? X molar, good. And then hydroxide is going to be 0 molar here because reaction 2 hasn't occurred yet. And then reaction 2, the change here is we're going to plus Y molar additional hydronium plus Y molar hydroxide. And so at equilibrium, we're going to get X plus Y molar hydronium and then Y molar hydroxide. So we have 2 unknowns. The 2 unknowns are X and Y. And so we need 2 equations to solve for 2 unknowns. And what are the 2 equations? The 2 equations are going to be, K for this is going to be Y plus X times X divided by 1 times 10 to the minus 8 minus X. That's 1. And then for reaction 2, we're going to get K is equal to X plus Y times Y. And so what's the usual way of solving these the 2 equations, 2 unknowns? You do substitution, but let me tell you, this substitution is going to be kind of weird. We'll substitute, let's say X plus Y. Now we'll solve for x plus y and then substitute into 1. This one, even though it might not look so difficult, is very difficult to solve algebraically. And so you can try it if you want to solve for x and y. It's not, lots of people do it. Solve for. It would be like a bonus, type scenario. You wouldn't have to solve for it, but if you did solve for it, it would be like a bonus. This is actually discussed in the book here. If you want to, the book goes through it. I'm not sure if I labeled everything just like the book did, but let me just check. So what we just did, example from 16.1 here, calculate a hydronium in an extremely dilute solution of strong acid. So 1 times 10 minus 8 molar HCl, although they use 2 sig figs, I only use 1 sig fig. So we just did that calculation. I set it up with 2 ice tables. They skip step 1, and they go straight to step 2. The second problem we just did is this one. (16.2), I think it was. 16.2, yeah. 16.2, how do we calculate the pH of a very dilute solution of a weak acid? And so they picked a generic acid, HA. I picked just hydrocyanic acid, HCN. And they use different symbols than I use here, because they're just doing it for any concentration. So the initial concentration is C. I gave you concentrations there. I set it up with ice tables. They skip the ice tables entirely and then just go to the algebra. I think they skip the ice. I think the book skips the ice tables usually just to save space. Yeah. But I think, if you set up the tables, it makes a bit more sense. Here they're working through how you solve this, algebraically. And so you should read this. You want to solve this. Actually, they don't really complete it. They just tell you, how to complete it here verbally, but they don't show you the steps, step by step. You could try it, see if you could do it. A lot of people can do this. So this is HCN. They picked 1 times 10 minus 5 molar. I did 1 times 10 minus 8 molar. And these are the numbers they got here. But, when we do these, do we have to do this? Do we have to do simultaneous? We have to do simultaneous in many different scenarios. It's not just the pH of a very dilute weak acid. We might have to do simultaneous when we have concentrated things as well, if they perturb the previous steps. So we'll see some scenarios with that occurring. All right, so those are some acid calculations here. Let's look at some base calculations and then pH in general.
So the only way to be able to do it algebraically as well?
This one?
Yeah.
Just solve the algebra. But the algebra is not so simple. So let's see what they recommend here. Let me see if I can find it. Yeah. Okay, let's just see here. Our next task is to solve this pair of equations simultaneously for x and y. Okay, good. Okay, they begin by rearranging things. All right, now we can use these two equations to rewrite the expression. So they substitute. So rearrange, note they're solving for x plus y and then substituting that here. Okay, and then they rearrange this here. Okay, now they substitute in the equation, then solve for x by using the method of successive approximation. So the math is too hard to solve. So you got to use the method of successive approximations discussed in Appendix A, and then you can come up with the answer. So you're going to be guessing and checking. That's because, you know, it seems easy, but it's not. I mean, this is not easy. And so we use this method of successive approximations. I don't know how many guesses it took, but then they finally got the answers here. All right. We try to avoid doing simultaneous, and so that's, for us, fortunately, most of the problems we do, we can just do stepwise, and that seems to work fine. And so let's look at an example of stepwise. Actually, before I get to bases, let's do, you said we want to do carbonic acid? Well, the problem with carbonic acid is we might have to do that on simultaneous. And so let's pick a different multiprotic acid. And so let's pick something easy like this. Something easy is kind of a high concentration. A high concentration, well, one thing it means is that the simplifying assumption might work. You know, if we start off with like 0.1 molar, 0.01 molar, 0.001 molar, then the simplifying assumption is less likely to work. But if we start off with, let's say, 1 molar, 2 molar, 3 molar, then the simplifying assumption is more likely to work. Well, they figured it out for this particular problem. They figured out what molarity will make the simplifying assumption work. And what they came up with is this. This is the example they do in class. Let's see this example. Here. They take 3.0 molar. Why are they taking 3.0? Because the simplifying assumption will work. If we go too far below 3, then it's going to fail. Above 3, it's fine. But above 3, if you go too far above 3, then you have to worry about effective concentration versus stoichiometric concentration. You have to worry about activities, and we should be using activities if we go too far. And so 3 is what they chose here. Now, phosphoric acid is a triprotic acid. Oops. And so let's take a look. Phosphoric acid is a triprotic acid, and if we look at the first hydrogen here on H3PO4, the first hydrogen, when we lose that, we're going to form H3O plus and dihydrogen phosphate. And the Ka value for this, which we call Ka for step 1, so this is step 1, is 7.1 times 10 minus 3. And then we can lose the second hydrogen. If we lose the second hydrogen, we take our dihydrogen phosphate to form monohydrogen phosphate. We lose that and create another hydronium. This is 10 to the minus 8. Now look at this. the first hydronium, or the first H plus, is much stronger, 5 orders of magnitude. 5 orders of magnitude is like 10,000 times stronger acid. So this is 10,000 times weaker. And by the time we get to the third hydrogen here, and we lose that to form hydronium phosphate, it's 10 to the minus 13. Now that's another 5 orders of 10,000 times weaker. And so when we're doing this, this is a good candidate for stepwise. This is a good candidate for stepwise because in step 1, we're going to produce the most, and then step 2 will produce a little bit, and step 3 will produce a little bit. The reason being is that if we just produce a little bit in the successive steps, then it's less likely to perturb the previous step. If we produce a lot in the successive steps, then it's much more likely to perturb the previous steps. And so let's look at some examples where it's more likely to perturb the previous step. Okay, here, if we look at H2S, is a diprotic acid, hydrosulfuric acid, or hydrogen sulfide. The first hydrogen, 10 to the minus 7, so it's pretty weak, it's like water. The second hydrogen, look at that, 10 to the minus 19, which is worse than water. So this is even less acidic than water. But when we look at it, will the second step likely perturb the first step? No, because we're going to produce so little hydronium, it's not really going to perturb it. If we look at carbonic acid, first step is 10 to the minus 7, second step is 10 to the minus 11, that's 4 orders of magnitude. It's probably not going to perturb it. But the problem with carbonic acid is the initial concentration. CO2 is not very soluble in water. And so carbonic acid, we can't get a very high concentration. Let's see what footnote B says and footnote A says. So footnote A, the value of Ka2, H2S, in the older literature is 10 to the minus 14, but current evidence is considerably smaller. So if you look in old books, it has a different Ka2 value. Okay, B, carbonic acid cannot be isolated. It is in equilibrium with water and dissolved CO2. The value given for Ka1 is actually for the reaction of CO2 plus water, yields hydronium and bicarbonate. Generally, aqueous solutions of CO2 are treated as if the CO2 were first converted to carbonic acid, followed by the ionization of carbonic acid. So this is another reason I skipped carbonic acid, because I didn't want to really get into this. Because, if we skip it, it'll make life easier until you have to do it. And then when you have to do it, then you just have to, unfortunately, deal with it. But we'll postpone that for as long as possible. Maybe we can postpone it to the end of the semester so we don't have to deal with this at all. Because with the CO2, then we have to get involved with Henry's law and the CO2 partial pressure above. There is already one tough problem in the book, which was the CO2 with radioactive carbon-14. That wasn't so easy. It was in yesterday's video. Let's see that. All right, so let's take a look at phosphoric acid, and I'm just going to kind of do what the book did, except I'm going to set it up the way I think you should set it up. Okay, are we out of time? Yeah, we're out of time. All right, so we'll stop here. Continue this Wednesday. So the lab, look for that today, and I'll talk about it tomorrow, the beginning of the lab.